Hello everybody, my name is Zineb. I am a chemical engineering student at Polytechnique Montréal, and this summer I had the opportunity to work on a project about the energetic demands for the production of metals, and I mainly focused on copper. A part of the project was to simulate the process using the FactSage software. So today I will be presenting the copper primary metal production from chalcopyrite. I will start with a brief introduction, an overview of the Noranda process, a simulation of the smelting unit, as well as the converting unit, and I will end with a short conclusion and I will take your questions if you have any. First, copper is known for its excellent electrical and heat conductivity, as well as its very good corrosion resistance. It is also 100% recyclable, and about 80% of copper that has been produced is still in use nowadays. Now, there are two ways to produce copper. Sulfide ores are extracted using pyrometallurgy, and oxide ores are extracted using hydrometallurgy. About 80% of copper from the mines are extracted using a pyrometallurgical process, which is what I will be talking about today. Now, there are multiple processes, but they all start and end in the same way. We first have a comminution step, which is used to crush the rocks that were mined into a fine powder. We then have the flotation, which is used to separate our ore from any impurities. Drying is used for flash smelting, direct to copper smelting, and teniente submerged 3-air smelter. Vertical land smelting and Noranda or horn smelter do not require drying before the smelting. We then have our converting unit, which is used to transform the matte from the smelting into blister copper. And we have the anode refining and casting, which uses air injection and hydrocarbon injection to remove sulfur and oxygen. Finally, we have electrorefining by electrolysis. I will be mainly focusing on the Noranda smelter or horn smelter. What's interesting about this smelter is that it can take metal-bearing electrical equipment as a feed. So I will be simulating the copper smelting, which transforms the wet chalcopyrite into a matte with a copper concentration of around 72 to 74%. And then I will be simulating the copper converting, which is separated in two stages. First, we're reducing the iron concentration in the matte to less than 1%, and then we are producing blister copper, which has a concentration of copper around 99%. First, for the copper smelting, what goes into our smelter is our copper ore that's exiting the flotation unit, so chalcopyrite plus around 8% of water, our flux, which is silica in this case, oxygen-enriched air, and what comes out is our off-gas, our slag, and our matte phase. All the percentages were found in Schlesinger's extractive metallurgy of copper. The main reactions that are happening in our smelter are the oxidation of our chalcopyrite, which produces our matte, iron oxide, and a gas. The iron oxide is then reacting with the silica to form phyalite, which forms our slag phase. Now, the reason we want to form a matte and a slag phase is that the two are immiscible, so they are easier to separate. The slag phase comes out from a tap hole at the side of the smelter, while the matte phase comes out from a tap hole at the bottom of the smelter. Going into Eclipse module in FactSage, I am using a calculation basis of 1 kilogram of wet chalcopyrite. So as you can see, 920 grams of chalcopyrite plus 80 grams of water. I have my oxygen-enriched air going in at a pressure of 1.6 bar, which is also a value found in extractive metallurgy of copper. And I have my silica. Now, as you can see, I put in here an alpha and a beta parameter, which are variable since I do not know the amount of air or silica that I need yet. A very important step before starting the calculation is to make sure that the units that are selected here are the ones that you want to work with for the rest of your simulation. Database selection is also very important. For the simulations that I will be doing today, the database selected are FactPS, FT-Oxide, and FT-MISC. FactPS is selected for gas and stoichiometric compounds. FT-Oxide is selected for oxides, so it will be useful for my slag phase. And FT-MISC is for miscellaneous sulfide phases, which will be useful for my matte phase. Now onto the product selection. I am selecting all gas species as well as pure solids, and I am also selecting all solution phases except FT-MISC Mat 2B, which is a hybrid solution that I do not want FactSage to consider in my calculation. I am then making alpha range from 0 to 800 and selecting my beta parameter at 0. My temperature of operation is 1250 degrees. Now calculating, this is the results page that I get, and you can go through all of these windows to see the effect that each alpha has on the chalcopyrite, but a better way to visualize your results is to plot them. So going here in output, plot results, this is the page that we obtain, and first thing to do is to choose the axis. So for this simulation, I chose weight percent solution species as well as my alpha, and you then have to select the species that you want to appear in your diagram. When plotting, this is what I got, and you can see as we are blowing air into the smelter, the copper concentration in the mat is going up while the one of iron is going down, and we are forming iron in the spinel phase, which is stabilizing. As I said before, we want a concentration of about 70% in the copper, which corresponds to 780 grams of air blowing. Now putting the value of 780 grams back here in this menu, and still putting beta at 0 because I just want to see the effect that the air has on our wet chalcopyrite. The results that I get is a matte with a copper concentration of 71%, a total of 448 grams total of matte, and 344 grams of spinel phase. Now, I do not want this spinel phase. Like I said before, I want a slag phase, and for this purpose, we are going back into FactSage main page and going here in documentation. We are searching for the iron oxide and silica phase diagram, and to obtain the phyolite, we are choosing the right mole ratio, which in this case is 0.33, and making the calculation to obtain the amount of silica needed to form our slag phase. Going back in here, we have our right amount of air blowing that we found with the graph showed before, and we have the calculated amount of silica needed to form our slag phase. Now running this calculation, this is what we obtain. We have our slag phase, 500 grams, and our matte phase, 410 grams with a copper concentration of 76%. Now our smelting is done, so we are moving on to our converting unit. And what is going in is our matte from the smelting unit, our flux, which is once again silica, oxygen-enriched air. What comes out is our blister copper, our off gas, as well as our slag. Now what I want to do is save the matte stream from the smelting simulation to use in the converting simulation. For this purpose, we're going into the results page of Equilib and going here into Output, Stream File, Save Stream File, Save Solutions, and we are selecting the matte phase, which you give a name, and I gave it matte from smelting as a name. Going back into the reactants page of Equilib, we're going in Edit, Mixtures and Streams, Import a Stream, and we are selecting matte from smelting. Now we have our matte from smelting, which is a total of 410 grams. We still have an alpha parameter here for our air and a beta parameter for our silica, since we have to determine these amounts, and it is still going at the same pressure and temperatures. Here for the final conditions, I am making my alpha parameter range from 0 to 100, beta parameter is still 0, and temperature of operation is 1300 degrees Celsius. Now this first part of the converting simulation is pretty much the same as the smelting simulation. We're plotting our results, and as we can see, the copper concentration in the mat doesn't change that much. Same thing for the sulfur concentration in the mat. We can see here that the iron concentration in the mat is stabilizing around alpha equals to 40. And we can see here that we are forming liquid copper, which we do not want. We want to keep just our matte and slack phase to be able to separate them. So we are choosing alpha equals to 40 since this is where the iron percentage is stabilizing and we still do not have any liquid copper. Now once again, finding the amount of spinel and using the same phase diagram and the same mole ratio, we are calculating the amount of silica that is needed, in this case 7 grams. Running the calculation, we obtain 384 grams of matte with a copper concentration of 80% and our slack phase total of 25.2 grams. Now moving on to the second part of the converting. Now what is done in the industry, it's either the matte is taken out of the converter and taken to another converter to start blowing air, or the slag phase is taken out of the first converter and we are doing our second part of the converting in the same converter. Now this doesn't change what I'm doing. In fact, I am still saving the matte stream from the converting, going here in output, stream file, save stream file, and we are saving our matte phase, which in this case I named matte from converting. Going back into our reactants page, we are importing the matte from converting in the same way as I did before, and we have our oxygen enriched air going at the same pressure and temperatures once again. Now here we are making alpha range from 0 to 200, same temperature since it is the same converter. And when plotting the results, this is what we obtain. We can see that the copper concentration in the matte is dropping significantly while the one in the liquid copper is increasing. And as we said, we want a copper concentration in the blister copper of around 99%. Now this corresponds to 181 grams of air blowing, and our final results are 312 grams of liquid copper with a copper concentration of around 99% like we wanted. Now, just as a reminder, we started with a calculation basis of 1 kilogram of wet chalcopyrite and we ended with 312 grams of liquid copper with a copper concentration of 99%. Now, I was able to simulate part of the process with minimal information found in the literature, and I believe that it is possible to play more with the parameters and use existing phase diagrams to build a process from the beginning. And while playing with the parameters like temperature of operation, you are able to find a certain equilibrium between the cost of operation and the efficiency of the process to build the perfect process. I will now be able to take your questions if you have any.